Hi, welcome to tutorial 6.5 part 1. In this tutorial we're just going to kind of get used to the idea of describing an atom in terms of the electrons that are sitting on the outside of the nucleus in something called atomic orbitals. And at first it'll feel a little bit like we're just kind of getting used to language. So let's try out this first question. How many electrons can fit in the n equals 2 energy level? So what are you supposed to be imagining about this atom? We imagine that the electrons in this particular atom can exist either in this first orbit, that we're actually not calling an orbit anymore but an energy level, or in this second Bohr type orbit, but actually we're calling it now a second energy level. This would be the third, quote, Bohr orbit or energy level now, or the fourth energy level. So what are these boxes supposed to represent? Those boxes represent orbitals, particular distribution patterns, probability distributions of how an electron can exist in that particular atom. Each box can hold 2 electrons, and they have to have opposite spin to occupy that particular orbital. So let's just go ahead and try to answer this question, get used to the language, and we can talk about later in class exactly what are we talking about here. But let's just get used to the language for now. Okay, second energy level, where am I? Well, I'm in the green box area. That's that kind of second region. We can see it here. It's these guys here. So we just count the number of boxes. I see 1, 2, 3, 4 boxes. They hold 2 electrons apiece. So the answer to the question is 8 electrons can occupy the second energy level because there are 4 orbitals holding 2 electrons apiece in that energy level. Now let's try another one. How many electrons can fit into the third? You say, well, all right, I get this. I just count the number of boxes. I look up here. I see how many boxes I have. That's exactly right. We can see that there are 1, 2, 3, 4, plus another 9 boxes. They hold 2 electrons apiece. So that's easy. 2 times 9 is 18 electrons fit in the third energy level. All right, one other type. Now here's a different question. How many subshells are there? So we're getting used to this language here, the language of subshells. So if this is no longer called an orbit but an energy level, there's another word we can use. It's called the shell, the first shell. In that same way of talking, this second energy level would be called the second shell, and it's broken up into 2 parts, 2 subshells. There's the S subshell and there's the P subshell. And notice the S subshell always holds 2 electrons and the P always 3. And if you kind of look at this and see the pattern, as we go up in energy levels, every time we go to another energy level, another shape becomes available. And each of these shapes are distribution patterns, probability distributions of how an electron exists on the outside of an atom. All right, so it's easy to say what the answer is. How many subshells are there in a second energy level? Well, you can see there's 2. So the pattern of it is described here. Every time we go to another energy level, another shell becomes available. And by the way, they are referenced by this L quantum number. Every time there's another L value, there is another shape available. Okay, so here's the final answer. We can also refer to these as the S and the P subshells. Last kind of question. Here it says how many orbitals are available. So we've been talking this whole time about orbitals, so it's just making sure we get the word orbitals in the third energy level. We counted them before. 1, 2, 3, 4 plus another 5. There are 9 orbitals. Didn't ask for the electrons. It didn't ask for subshells. It said how many actual orbitals are there, and the answer was just 9. Okay, that's all there is to this. It's just getting used to which words: shell, subshell, orbitals, and how many electrons fit in the particular orbitals when you're looking at a diagram like this. So I think you'll have very little trouble with this on the quiz. It's just getting used to language. What it actually means, what you're supposed to actually conceptually visualize about these atoms, is of course quite a bit more difficult. But we'll keep working on it. We'll get it together in class. All right, see you there. Bye.